Hello students. Uh, Good morning all of you. We have been developing the beam element according to the FEM formulation. A beam element has two nodes. Each node has 2 degrees of freedom, one corresponding to the transverse displacement and the other degree of freedom corresponding to the angular rotation. Now on the basis of this, we have developed the stiffness matrix for the beam element. In fact, we have used the um, knowledge which we have acquired from the elementary strength of material lectures to derive the relationship between the forces and moments against the transfer displacement and the angular rotation. So for deriving these equations, we have used the knowledge of elementary strength of materials. Now, depending upon these uh, equations, the next step was the sign convention. In fact, the sign convention which is followed in the traditional SOM approach and the FEM approach, they have been discussed. In fact, they are not the same. So depending upon the sign conventions, we transferred the relationship obtained from strength of materials to the equivalent relationship which are going to be applied in finite element. This much of the work we have already done in the previous classes. These equations obviously were applicable for a point force and point moment. But the thing is that since a beam is capable of supporting a distributed load also, so somehow the distributed load is supposed to be transferred to equivalent loads acting at the nodes. So this is the topic which we are going to discuss today. In fact, we are going to use the SOM theory for these um, transfer of loads also. We are going to use the SOM theory for transferring the distributed load acting over the domain of the beam to equivalent load acting on the nodes. The stiffness matrix developed is for point moment and forces applied at the node, but beams can support distributed loading as well as concentrated nodal loading. The distributed loading is converted to statically equivalent loads acting at the nodes. This is explained in the next slides. The distributed load acting on the beam can be converted to equivalent loads acting on the nodes by any of the following two approaches. The first approach happens to be statically equivalent forces. In fact, this is what you have studied in your BTech classes. And the second approach happens to be the work equivalent method. Now coming to the first approach, so we have a beam. Uh, in the present example, it is a fixed beam. Both the ends are fixed. The length of the beam happens to be capital L, and the beam is subjected to UDL of intensity W pounds per fit. Now, when the this load acting is supposed to be transferred to the nodes, what we simply do is that we simply find out the reactions at the two nodes, and then we invert the reactions. That is, we invert the reaction. So obviously it means that the nodal load are going to be statically equivalent to the distributed loads. So all you have to do in this particular approach is that irrespective of the type of loading which is being given, you simply find out the reactions or the resultant forces acting at the nodes, and you reverse their direction. Both the statically equivalent concentrated nodal forces and moments and the original distributed load have the same resultant force and same moment acting about any arbitrary chosen point. These statically equivalent forces are always of opposite sign from the fixed end reactions. So basically the process is that for the given load, you find the reactions at the supports, and once the reactions have been found, you simply invert or reverse their direction. So this approach obviously is one approach which you have already studied in your BTech classes, since you have done plenty of examples of this particular type. The second approach happens to be the work equivalent method, and the basic concept behind this particular approach is that you find the work done by the distributed loading, and you find the work done by the forces and the moments acting at the nodes, and both these work done are supposed to be equal. So you are basically conserving the energy. We can use the work equivalence method to replace a distributed load by a set of discrete loads. So we are replacing a distributed load with a discrete load. This method is based on the concept that the work of the distributed load in going through a displacement field represented by Vx is equal to the work done by the nodal forces and moments in going through nodal displacements for arbitrary nodal displacements. So the basic concept is that the amount of work done by the distributed load and the amount of work done by the nodal loads, both these works are equal for arbitrary displacements. So this is the theory behind it. So we have a load distributed arbitrary distributed load acting on the beam, and it has to be converted into a equivalent nodal system. Please notice that the direction of forces and the direction of movements and obviously displacements and angular motions are according to the sign conventions which we are now going to follow for the FEM beam element and not for the according to the SOM. So the distributed load obviously is going to be the integral of the load multiplied by the transfer displacement integrated over the entire domain. So equation number 1 gives us the distributed load. But for finding the discrete load, that is finding the work done by the discrete loads acting at the nodes, we simply multiply the moment and the corresponding angular rotation. So we have two terms corresponding to moment multiplied by angular rotations and two terms corresponding to force multiplied by transfer displacement. This obviously is um, the discrete work. So we get the total amount of work done because of distributed load and the total amount of work done by the distributed load. And in the next slide, we, we simply equate them. We can determine the nodal forces and moments used to replace the distributed load by using the concept of equivalence. That is by setting W distributed is equal to W discrete. So we have calculated distributed load, distributed work done, We have calculated discrete work done, and we already have an expression for the transverse displacement. This is a displacement this is the equation for the transverse displacement which we have already derived earlier. So for this particular example of a cantilever which has a UDL of intensity W, we are simply going to evaluate the nodal loads. So when we know the value of UDL, that is W, and when we know the expression for the transverse displacement, we simply evaluate expression number 1. We substitute the value of V from expression number 2 to expression number 1 and carry out the required integration. This gives us the value of distributed work done and is written in expression number 3. But the discrete work done obviously is given by equation number 2. We simply compare the terms of equation number 1 and equation number 2 and find that m1 is given by expression number 3. Similarly, m2, which is the moment acting at node number 2, f1 and f2, which are the two forces acting at node number 1 and node number 2. In fact, the thing is that a wide range of loading have already been converted to equivalent loads on the nodes, and some of these cases have been shown in the next two slides. So we have 6 cases of loading being converted to discrete loads in the present slide, and another 3 cases in the next slide, which is on display at the moment. Now I'm leaving one topic as an assignment to be done under uh, self-study, that is beam elements with hinge. Quite a number of times we have beams which are connected to each other with respect to a hinge. They have a pin joint. So this particular topic is given to you as an assignment. So kindly go through it from the uh, book which you have at your disposal. In the next lecture, next topic, we are going to discuss the potential energy approach to derive the beam element equation. Potential energy approach obviously happens to be a more versatile approach for finding the stiffness matrix, and this we have already discussed. This particular approach we have already discussed for a bar element in the previous classes. So we have a beam which is subjected to surface load given by T. It is since this particular surface load is acting in the y direction, it is indicated by Ty. The length of the beam element obviously is capital L, and there happens to be point loads and point moments acting on the nodal locations, and the direction of the coordinate system is also indicated. Now potential energy obviously is one thing which you already know. It is the summation of internal strain energy indicated by U, and the corresponding external energy because of loading denoted by omega. So the potential energy happens to be the summation of the internal and the external energy. So we have equation number 1 as the summation of the total energy. The strain energy is obviously the integration of stress multiplied by strains, and the integration is supposed to be carried out over the entire domain. This is equation number 2. Please note that the same equation, that is the same formula, was being used for finding the internal straining energy for the case of bar also. This is because both bar and the beam primarily have only uh, the stresses and strains acting along the x direction. Um, Other stress and strain happens to be of no significance. This obviously comes from the elementary SOM theory. Now, after we have evaluated the internal strain energy, we come to the external energy because of forces. Since there happen to be three type of loading on the beam element, we have a surface load indicated by T, we have a point load indicated by P, and we also have moments indicated by M. In fact, uh, the work done by the surface load is going to be evaluated when we carry out the integration over the surface area. And since there are 2 point loads and two moments, uh, the value of I in both these expression in both these evaluations varies from 1 to 2. This is because we have 2 point loads and two moments. So this gives us the external energy. And if you follow the matrix formulation, the loading on the beam is expressed as F1 M1 F2 M2. This basically is a column matrix given in expression in equation number 4, and the degree of freedom in equation number 5. We can have a alternate expression for the external energy, and also notice that we are using a transpose of D matrix. So that this basically comes from the rules which are supposed to be followed for the matrix multiplication. We are taking the transpose of the first matrix, and the P matrix remain a column matrix. This is equation number 6. So we have four equations which have been carried forward from the previous slide. Equation number 1 corresponding to the potential energy, total potential energy. Equation number 2 for the internal strain energy, and equation number 3 for the um, discrete energy, that is due to the external forces. And then we obviously make some simplifications, because in a beam element we basically uh, find that the stresses and strains are one dimensional, others are not existing. So we basically convert the volume integral to a equivalent line integral, for which we represent elemental volume dV as dA into dx. This is equation number 4. And similarly, the surface area has also been simplified as ds is equal to b multiplied by dx, where b happens to be width of the beam. Since stresses and strain are not varying uh, along the depth of the beam element, this is equation number. This gives us equation number 5. And here comes a difference between a bar element and a beam element. In the bar element, if you know the displacement field, you simply find its differential to get the expression for strain. But in this particular case, since the beam tends to bend, since the beam tends to bend, the strain basically is going to depend upon the distance of any member from the neutral axis. So it basically is depending upon if y happens to be that particular distance, the strain depends upon y. So this is why the term y is coming in expression number 6. This obviously has been derived in your elementary SOM theory. So we need not discuss why there is a term appearing corresponding to the second differential of v and why there is not a first differential of v. So I am sure that these topics are these are some of the theoretical topics which have been covered in your previous SOM classes. So we basically move forward, and in the matrix form we have equation number 7, in which the B matrix basically represents the differentials of the shape functions to give you a strain. A similar B matrix was used in the case of bar also. So those of you who are feeling somewhat out of place, they can refer to the lectures of bar, where we have uh, differentiated the shape functions to get the matrix B. In this case, the individual elements of B are going to be obtained by the second differential of the shape functions. This is because the term V is being differentiated twice in expression number 6. So B is going to contain the terms corresponding to shape functions which have been differentiated twice. But I'm not giving you the matrix corresponding to B. This is one thing which you are supposed to evaluate on your own. And then once the strain matrix is known, you simply multiply it by the um, elasticity equations to get equivalent stresses. And for a beam element, that is a one-dimensional case, the elasticity matrix D simply happens to be elasticity itself. It is a matrix of size 1 by 1. But in cases such as plane strain and plane stress, we will see that the matrix D happens to be of size 3 by 3 or 4 by 4 or even 6 by 6 by 6. But for the time being, the D matrix, which relates stresses to strain, simply is a one-dimension matrix, 1 by 1 matrix, and it is equal to elasticity itself. This is equation number 9. And as a result, what you get is equation number 10, which relates the stresses against the degrees of freedom. So you have equation number 7, which relates strain to degrees of freedom, and you have equation number 10, which relates stresses to degrees of freedom. Both these expressions, that is equation number 7 and equation number 10, are going to be substituted in equation number 2 to evaluate the total uh, internal strain energy. Of course, equation number 4 and 5 are also going to turn up, which is going to convert the volume integration into a line integration. That is a one dimension integration. So we have equation number 1, 2, 3 and 4, which have been carried forward from the previous equations. We have equation number 5, which is the total energy of the beam element, summation of internal and the external forces. And then this is the volume integral converted into a equivalent one dimension integration. And in matrix form, we take the transpose of the stress matrix. This is the first term. And we take the transpose of the D matrix. This is the second and the third term. and then we simply substitute the value of stress and strains and shape functions and degrees of freedom in equation number 7 to get equation number 8. And we start with equation number 8, which is equation number 0 now. In equation number 1, the transpose has been transferred from outside the bracket to inside the brackets. So the order of multiplication of the matrix becomes reverse, and all the matrix now are going to have a transpose also. This is equation number 1. And here is a point which in fact um, comes from the elementary sum theory. The thing is that the thing is that the first term on the right of equation number 1, the first term in the right of equation number 1 has a elemental area represented by dA multiplied by y square, and there is a integration sign. So this basically means that the elemental area, that we are finding the second moment of the elemental area, which basically is moment of inertia itself. Therefore the terms dA, matlab y square dA, which exists in equation number 1 has been replaced by moment of inertia indicated by capital I, and correspondingly the volume integral is now replaced as a line integral, that is a domain represented by dx. And once we know the energy, obviously the next step is to minimize it. So we simply differentiate equation number 2 with respect to the unknowns, which are represented by degrees of freedom, that is matrix D. And in the second term on the right, it has to be a line integral. So the symbol corresponding to the line integral is wrong. I have mistaken. This basically happens to be a typing mistake. There has to be a line integral in place of the area integral in the second term on the right. This is equation number 3. Now, one other point is that the the steps involved in the differentiation of equation number 2, obviously they are missing over here. But the thing is that a similar differentiation was carried out for a bar element in the previous lectures, and all the steps involved in differentiation were told to you, they were discussed in detail in that particular lecture. So there is no point in repeating the differentiation steps again and again, and obviously they have been missed out to give the final expression. Obviously the steps of differentiation, they should be known to you. So I expect that all of you are going to carry out the differentiation on their own and will do the steps which are missing in between. Carrying on with the lecture. This is equation number 0, in fact derived in the earlier class, in the earlier slide. So we have simply simplified. E happens to be a constant quantity. I also happens to be a constant quantity. So these two terms have been transferred outside the integration, because E and I do not depend upon, they are constant quantity, they do not depend upon x. So obviously they have been transferred outside. So we get equation number 1, which now becomes the governing equation for the beam element given in equation number 0, where K is the stiffness matrix represented by EI divided by 2, and the integration of B transpose into B dx, integration of this particular term represented in equation number 3. And similarly, the force now is going to be the summation of forces acting at the loads, acting at the points, and the summation of the equivalent load, equivalent distributed load when transferred to the nodes. So equation number 4 basically is the summation of the point loads acting at the nodes and the equivalent load, equivalent load because of the distributed loading transferred to the nodes itself. So this is equation number 4. And the shape functions given by equation number 5, 6, 7 and 8, in fact they have been derived earlier uh, in the lecture when we were discussing the uh, a cubic polynomial to represent the displacement field. So we basically know the shape functions also. Now the stiffness term, which is given by equation number 1, and the force term given by equation number 2. Here we are simply going to substitute the matrix B in equation number 1, and this is going to give us the stiffness matrix, which is on display now. Basically, it is the same matrix which we have derived earlier using the other approaches. But now the derivation has been done using the potential energy method. And in the next slide, we are going to do the same derivation, but that particular derivation is going to be done using the Gallakin approach. Now, enough has been discussed regarding the Gallakin methods, so we need not discuss all those points, all the procedural steps for the Gallakin method. So I'm just skipping forward. All these things we have already discussed, so there is no point in discussing these terms again and again. I'm sure by now all of you already know what the Gallakin method is. So I'm just skipping through the lecture contents one by one. Now equation number 4, equation number 1 on display happens to be the required governing equation. It is a fourth order differential equation. Therefore, the method of integration by parts, which basically is done for reducing the order of differential, is going to be applied twice. When we apply this method for the first time, the fourth order term is going to be reduced to third order, and we are going to get the first boundary term. And when we apply the integration by part approach for the second time, we are going to reduce the third differential to the first differential, and we are going to get a second boundary term. So the thing is that because we have a fourth order differential equation, the integration of part is going to be applied twice, and we are going to get two boundary terms as a result. So this is equation number 2, which is the required statement for the Galerkin approach. We have equation number 3, which is the displacement field expressed as a function of degrees of freedom. We already know expression number 4, and the required shape functions are already have been derived earlier. Now a quick review of the integration by parts approach. We have two functions a and b, both are functions of x. We differentiate them and then we integrate them, and this gives us the final expression, which is supposed to be applied to the reduction of the fourth order term. So we have the differential equation indicated by equation 0 and the corresponding equation number 1, which comes from the integration by parts. And equation number 2, this is basically equation number 0 written once again. So if you compare equation number 0 and equation number 2, you find that the fourth differential of v has been split into two terms, and then you can compare to find that a can be written as the cubic differential and b can be represented as ei into ni. This is equation number 3 and equation number 4. Now this 3 and 4 are going to be substituted in equation number 1 to give equation number 5, where the term a appears at three places. This is place number 1, place number 2, and place number 3. And similarly, the term b also appears at three places. This is the first place indicated in red, second place in red, and the third place. And then we are simply going to transfer the term of equation number 5 to get equation number 6. So what has been done here is that when you reduce the fourth order term, you basically get a third order term and a term which is supposed to be evaluated at the boundaries. This is equation number 6. Now in the next slide, we are going to reduce the order of the third order term, which appears in equation number 6. These steps obviously are going to be same. So we start with equation number 1. We are supposed to reduce the third order term. So the third order term has been split into two. So this becomes A and this becomes B, given by equation number 4 and equation number 5. And then we substitute the value of A and B in equation number 2 to get equation number 6, where A appears at three places as it did in the earlier slide, and B also appear at three places in the present derivation. And in the next step, we simply readjust the terms of equation number 6. So we now have the reduction of the third order derivative. In fact, now we have a second order derivative, which is in equation number 7, which is the second term in equation number 7, and a boundary term, which is the first term on the right of equation number 7. Now we are simply going to substitute, we are simply going to gather all the equations required at one place. So this is the required governing equation. This is the reduction of the fourth order to the third order and the third order to the second order. And when we do all these substitutions, we basically are going to substitute equation number 3 into equation number 4, equation number 2, and the resulting equation is going to be substituted in equation number 1. This gives us the final expression in equation number 4. And then equation number 5, which is the uh, going to be rearranged to give the required governing equation. In this equation number 2, all the unknown parameters, obviously the displacement field V happens to be unknown, so that particular term has been kept in the left, and all the other parameters, they have been kept at the right. The loading on the beam indicated by W, obviously since it is a known parameter, it is kept on the right, and the value of d square v by dx square and d cube v by d cube x, they are supposed to be supplied as a boundary condition, so obviously they are going to be known, therefore they also have been kept in the right hand side. Now in the next slide, we are simply going to in the next slide we are simply going to expand equation number 1 to get the final form of the stiffness matrix. But as far as the derivation is concerned, the derivation is over now. Now, if you're supposed to expand, we basically require the second differential of the displacement field indicated by equation number 1. And since n1, n2, n3, and n4 are already known, we simply are going to take the second differential of these 4 equations, which are then going to be substituted in equation number 0. So these are the second differentials, and this means v comma xx. That means that the polynomial indicated by v has been differentiated twice with respect to x. So therefore we are using a notation v comma xx. V comma xx is going to be given by expression number 3, which in expanded equation form is equation number 4, or in matrix notation given by equation number 5, or in a more simplified form it is equation number 6. Here also a B matrix appears. In fact, this is the same matrix which appeared in the earlier derivation also, but the terms of matrix B were not disclosed. So B matrix basically is a matrix which relates the nodal degree of freedom to the second differential of the displacement field. In the next slide, we will explain the beam equations derived in the previous slides. So equation number 1 is the required differential equation. We are going to derive the terms existing in the left hand side first. For I to be 1, obviously the value of I is supposed to vary from 1 to 4, which is going to give us 4 simultaneous equations, linear simultaneous equations. For the value of I to be 1, we get expression number 2, which in expanded form is expression number 3. We simply have substituted the second order differential of V to get expression number 3. So coming to the next equation for I to be 2, and then for I to be 3 and for I to be 4. This gives us the left hand side of the 4 equations, and all these 4 equations together are equation number 1, 2, 3 and 4 on display. These are the left hand side of the 4 equations. The entire equation is yet to be developed. These simply are the left hand side of the 4 equations, which obviously can be written in a matrix form. And as you can see that this happens to be a matrix of size 4 by 4. Obviously, it has to be a matrix of size 4 by 4 because there are 4 unknowns, V1, Phi1, V2 and Phi2, corresponding to the 2 degrees of freedom at 2 nodes. And as you can observe, this also happens to be a symmetrical matrix. Now coming to the right hand side now, what should be noticed is that the term d square v dx square into ei, this basically is the moment, and the term dqv dx square into ei, this basically is the shear force. So I am replacing the second differential and the third differential existing in equation number 1 by moments and shear forces in equation number 2. And equation number 3 simply is the expanded form of equation number 2. We have two terms of moments which are supposed to be evaluated at x is equal to L and x is equal to 0. And also we have two terms corresponding to the shear forces which are supposed to be evaluated at x is equal to L and x is equal to 0. Obviously, these values of moments and shear forces, they are going to be supplied in the form of boundary conditions by the user himself. So they are going to be known parameters. So this is equation number 1, which has been carried forward from the previous slide. And these are the value of 4 shape functions at x is equal to 0 and x is equal to L. This is equation number 2 and equation number 3. And similarly, the differentials of shape function with respect to x evaluated at x is equal to 0 and x is equal to L. This is equation number 4 and 5. Because you see that there is a term of differentiation of shape function which is multiplied by m, and similarly the shape function itself is going to be multiplied by v. So obviously we are going to require the value of shape functions itself and the value of the differential of shape functions. So we have expressions 2, 3, 4 and 5. Now coming to I to be 1, we simply substitute the value I at 4 places, giving equation number 6, and then the resulting equation number 7. Now, equation number 7 has been obtained by substituting the value of n1 and dn1 by dx at x is equal to 0 and x is equal to L in equation number 6. For example, talking about the value of dn1 by dx at x is equal to L. dn1 by dx at x is equal to L is going to be found from equation number 5. So this is equation number 5, and the corresponding value is going to be 0. So the first term disappears. Similarly, dn1 by dx at x is equal to 0 is going to be found by equation number 4. This also is going to be 0. Coming to the third term, which has n1 evaluated at x is equal to L, this is going to be found from equation number 3, which itself is 0. And the last term is value of n1 at x is equal to L is going to be found from equation number 2. In fact, it is 1. So in equation number 1, we simply now get the fourth term and the fifth term, and the first, second, and third term simply are 0. So this is how you reduce equation number 6 to a corresponding equation number 7. And following the same steps, you get the equivalent expression for equation number for I to be 2, I to be 3, and I to be 4. And keeping all these terms together, that is placing the left hand side and the right hand sides all together, you get the equation on display. So the left hand side, obviously they are the unknown terms because they are to be evaluated, but the right hand side of the four equations, they are going to they have to be supplied from the user. The value of shape function n1, n2, n3, and n4 obviously is a known quantity expressed in a polynomial form, and the value of w, which happens to be the external loading, obviously it is known quantity. And then the user is supposed to supply the value of moments or the value of shear forces in form of the boundary condition. So depending upon which value is being supplied, that particular term is going to be known, and the other term obviously is not supplied, so that is not going to be known. So the net result is that we know the right hand side of some of the equations, and we do not know the right hand side of the remaining equations. So obviously the equations for which the right hand side is not known, they cannot be used, so they go out of the picture, and only the equations for which the right hand side is known, which is supplied in the form of a boundary condition that happens to be a known parameter, known quantity, so that can be used for finding the value of the um, degrees of freedom. So this in fact happens to be a general process which is going to be applied, which is going to be used. And in the next lecture, we are going to take an example for finding this particular solution. And please remember that we have already taken an example in the previous lecture. We have taken an example of a bar element of a cantilever, which was divided into two elements and three nodes. So basically, we can refer to that particular solved example also for understanding how the stiffness matrix is going to be used for solving the unknown parameters. So this is where we end the lecture and this particular topic. And in fact, since we have derived the equation of the beam element using three approaches, we have used the direct approach, direct stiffness approach, we have used the potential energy approach, and we have also used the Galerkin approach, which obviously are the three approaches which are going to be used for finding the stiffness matrix. So as far as this particular topic is concerned, this is also over now. And in the next lecture, we are most probably going to start with plane stresses and plane strain, where all the formulations are going to be done in matrix approach, for which the requirement basically is that your lectures of bar element and the beam element, they should be on your tips. All the derivation steps have to be all your tips, because once because in the case of plane stress and plane strain examples, we are going to do the entire derivation using the matrix approach. Okay, then this is where we take off. Thank you.